We are recording, and if I can move this out of the way, there we go. So, if you guys have any immediate concerns, let me know. If not, save them there during the class or after the class, whenever you guys want to chat. Just you guys know me; it's all good. Quiz 3 will go out there. Hi, Mallory. And quiz 3 will go out there this afternoon after class. It's ready to go. I've just put the paper copy out there so you guys can work on it. And I'm hoping there by tonight or tomorrow morning I'll have the e-copy of the quiz, which I'll just call the answer portal or whatever you do it, however you want to do it. And that'll be up. Quiz needs to be done before class next Tuesday, because we'll have class there next Tuesday, and then test 3 will open up. And don't worry about time. You'll have lots of time. Either it'll be open for 12 hours again, or it'll be a take-home assignment or something like that. So, but be ready to go for the test next Tuesday, 24 hours. 7 days from now exactly, be ready to go for your test 3. It covers what? 7, 8, and 9. So week 7, that was water. States of matter. You remember heat of vaporization, heat of fusion, Archimedes' principle, Bernoulli's, the buoyancy of water, the buoyant force there. That kind of stuff. Week 8, which was last week, was heat. What did we deal with? Q is equal to MC delta T. Remember, we dealt with the length of metals, like you have a bridge or something like that. The metal will expand, and every metal has its own expansion coefficient. The formulas that you'll need are posted there for this week. There's all your week 7 formulas there, okay? And there's your heat formulas there you'll need. And then these are the formulas there from this week. This one here is an old formula. Velocity is equal to distance divided by time. And these guys here. It's not a bad week at all. You can see these are little rinky-dinky formulas. You just plug and play. Okay? So these are the formulas there you'll need for the test. Quiz 3 goes out this afternoon. You'll have a week to do it. Same thing, answers need to be put up into the answer portal, but you guys will have a paper copy there so that you guys can just tootle around there for the week and answer questions. And then when you're ready to upload, it's bang, 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 bang. So I hope you guys are doing very well. Yeah, I got nothing. If you got nothing, the lab is due, next Monday. We had that little lab there. If you managed to miss yesterday's tutorial on the lab, quite frankly, I watched the videos. There's 1, 2, and 3. Please watch them in that order. And I watched the videos and just kind of reiterated it to you. The lab itself is completely unrelated to any previous curriculum we've had or any curriculum there that we will have. There are some, formulas there that you will need from early on, but they're not difficult at all. Today I'm going to explain some of the things in the lab. You'll see some of the terminology there, like period is time, and you're going to see frequency and wavelength. The lab will make more sense after today's class. Anything else? Lab, the quiz goes out. Next week is your test. The quiz covers everything. Well, I can't cover everything in a test. That's the ironic thing about a test, is that you see all this information there that we teach you. It's like so much information. There's thousands of words on my shoulders. But really, all I can do is ask you, a small number of questions, and hopefully that is a representation of what I've taught you, or what I've provided you to learn. And it's impossible. So you'll see there that the quiz, it covers everything from that, or it has questions from every unit, 7, 8, and 9. 9 you're just going to do there today. So practice the questions there that I've posted on today. All right. And today we're going to be dealing with waves and sound. So, and here are some questions here. There are the answers. Everything is there. Please try them out before attempting the quiz that will be released there today. Okay? And you have time. You have a week to do the quiz, so you have time to putter around and practice up. Okay? And the test there next week, I think it'll follow along the same lines. Yes, there will be matching. I'm going to try and see if I can clean things up a little bit as far as the matching goes. And that's what we're looking for there. Okay, there will be true and false. There'll be multiple choice. I like the matching because it's definition related. And there was no harm, no foul there on the last test, but I'd like to try and get a test where people are pulling their hair out. All right, so I'll work on the matching. There'll be true and false. There'll be multiple choice. Of course, there'll be calculations. So please do all the review questions I give you there every week. There's a reason for that. Any type of definitions there that you see, like heat of fusion, heat of vaporization, these kinds of things. What do they mean? And be prepared to pull them out there for a testing situation, okay? Really nothing special, just a humdrum test. And other than that, if you guys don't have anything, that's pretty much it for me. And we'll just continue on. Yeah. Are we good? Let's go. Waves and sound. That's what we're doing right there. Okay, so this will be the last lecture that'll be on test 3. Okay, and then after that, there's only what? Yeah, next week we have a lecture, week 11 and week 12, and that's it. We're almost done. You're almost done pre-health. Keep at it. All right. I am going to play this video because I think the movie is super cool. Of course, there's going to be a commercial. Oh, no, there's not.
Mission abort. Explorer, this is Kowalski confirming visual contact with debris. Debris is from a BSE sat. Repeat. I have
Dr. Stone requesting faster transport.
We have to go. We have to go. Go, go.
Reports meteorological conditions. Go, go.
Houston, Explorer, copy. Explorer, Dr. Stone requesting faster transport to Bay Area. Explorer, do you copy?
Explorer, permission to retrieve Dr. Stone.
Here goes one. Houston, Explorer, copy.
All right.
We've lost Houston. We've lost Houston.
Look, we need to get the hell out of here. Some help there, man? No, don't wait for us.
I'm stuck.
Man down.
Houston,
Man down.
Explorer, copy.
Explorer's been hit. Explorer, Explorer. Astronaut is off structure. Dr. Stone is off structure. Dr. Stone detached. Must detach. If you don't detach, that arm's going to carry you too far. Listen to my voice. You need to focus. I'm losing visual of you. In 2 seconds, I won't be able to track you. You need to detach. I can't see you anymore. Do it now. Houston, I've lost visual, Dr. Stone. Houston, I've lost visual.
Okay. Hopefully you guys are still there. The That movie, Gravity, awesome. But you'll notice there that a lot of space movies, Star Wars, Star Trek, and all this kind of, when the spaceship is flying through the nothingness of space, there's always this sound. And in space, there isn't. There's nothing there. That is the definition of space. It's should be referred to as empty space. There's nothing there. And yes, there's the occasional atom floating here and floating over there, but nothing here like on Earth, right? So there's no medium for waves to carry anything. And you'll see there in the whole definition of what a wave is and all this kind of stuff, which we'll get there, you'll see how that Gravity commercial video there from YouTube is more of a representation of what actually goes on in space than because there wouldn't be any sound. Sure, they'd have sound coming through their headsets, they have a microphone in their helmet and all that, but anything like that would not be transmittable through space. And we'll show you why, and we'll tell you why. Waves. And by the way, if you have a question, just turn your microphone on and just say, because I can't really see, I have the dialog box closed. Waves. Traveling disturbances consisting of a coordinated vibration that transmits energy with actually no net movement of matter. Interesting. So the matter really doesn't move. The matter kind of vibrates, and in that process, energy is transmitted. And a really good slide here I have towards the end is, I don't know if you guys probably wouldn't, but I'm sure you guys are aware of that there was a massive tsunami. There was a Boxing Day 2004, and I had just come back from that part of the planet, and this is on the Indian Ocean, and they had an earthquake off the coast of Indonesia on the Indian Ocean side, not the Pacific, and I think it was a 9 or 9.2, just massive, and just the ripple effect. There were the wave cascaded out from Indonesia towards all the other countries and continents on the Indian Ocean. So you have India, you have the Arabian Gulf, you have Sri Lanka, you have all of Micronesia, you had Africa, and you'll see just the absolute devastation. And you'll see there that as the wave was traveling through the water to all these other countries, there really is no net movement of any particle. And we'll show you this there. The disturbance is frequently called an oscillation. So an oscillation is basically one revolution. Okay? And this is basically a typical wave. Okay? And this is your crest. Okay? And these are your depressions in here. And you'll see basically we measure one wavelength. Okay, this is your crest, your trough. These are nodes. Okay, right here. And you'll see here that basically we can measure a wavelength from here to here. And that's your symbol there for wavelength. It's lambda. Okay. Or you could measure a wavelength, like they measured it here, from a crest to a crest. You could measure it from a trough to a trough, or you could even measure it from a node to another node. It's all the same thing. So however you however you see it, that's a wavelength. These waves, they travel through air, water, even, when you have it would have been a good thing if I would have had a real glass. You know how you have a glass, or I guess you could even have a see-through plastic cup with water, and you put a straw in it. and you look at it from the side, and you'll see there that your straw doesn't look like that. It looks kind of bent. And we'll get there when we get into light, and I think that's the last week there. And but it's quite interesting to see waves and compare them traveling through different mediums. And medium, that's what I wanted to introduce you there. It's just another word for whatever the wave is traveling through. So I'm just going to open my window. There we go. Get some oxygen in here. So, a couple of key words there: medium, oscillation, wavelength, and amplitude. Now, amplitude is the distance, okay, or the amount, okay, from zero here, okay? It's the amount of displacement. So if you had a bigger amplitude, this would go up and then come down even farther, okay? A smaller amplitude, you'll see there it gets shorter and shorter. So wavelength, amplitude, medium, oscillation. There's another one there, node, okay? We got lots of them here. Some waves we can see, like ripples on the water. Some waves we can feel, earthquakes, my neighbor's loud bass. Some waves we can sense, light waves, heat waves, okay? But waves all share a few basic principles, okay? All waves involve some type of vibration or oscillation. Some of them, okay, will look like that. Some of them, okay, they go like that. But there is still this oscillation or this vibration, okay? All waves move and carry energy, but they don't have any mass. So this is where the scientific community is still kind of out to lunch. They don't know, you've got light waves that kind of act like a particle. And as long as something, what we mean is something acts like a particle, means that now this thing has mass. And if things have mass and occupy space, well then, other things happen. Okay? And things that don't have mass, okay, then other things happen. But you'll see here that like light waves there, photons, these kinds of things, they kind of act like they have mass, but they don't. And again, we could do 10 PhDs on this. We're just kind of skimming the surface there. And if you didn't attend the tutorial there yesterday, and if you had a look at the lab, you're probably going, "What? We didn't cover this? What's going on?" And you're right. Nobody's covered it. This is completely new. It's not really part of the curriculum. It's put in there because, number one, the ministry requires it, and number two, it's all about critical thinking. And we kind of throw this in there. We don't do it week 1. We do it week 9 or 10 and get you guys, wham, just something, it's completely relevant, but it's completely new. And with new formulas and all that, we just want to see how you can cope with it. There are a couple graphs in there. Graphing is important where you guys are going, so that's that. So the sound of a loudspeaker can break a wine glass even though nothing moved, right? If you have a look here, I apologize for the wordiness. This is a good slide, though. There are some good things in here, okay? I just didn't want to break it up into 2 slides because then double my work. A wave is a transmission of energy from one place to another. Okay, so individual medium particles are displaced by a disturbance, and then they return to their equilibrium position. Okay, just breaking that down. The individual medium particles. So here we're talking the air molecules or the water molecules. Those are the ones that are moving. And the wave is taking them with them, bringing them up, displacing them, and then returning them back to normal. And that's how it's moving on. And then even on the downside, in what we call a trough, it's displacing. They're displacing them and then moving them back to normal. So they don't move at the end of the day. All right. And energy is transferred from one particle to the next. So from atom to atom to atom to atom. And so basically it's the energy moves, but the individual particles do not. And you just have a look here at the example. And this is where the picture is. And a rope held tight between two people, and a flick of the wrist will initiate a wave pulse down the rope. And each segment of the rope is pulled upward in turn. So you see, you give it a flick, and then this wave pulse will go down. Okay? And each segment of the rope is pulled upward in turn by its neighboring segment, thus passing on the energy transmission, but it always returns to normal. Okay? So, the electromagnetic spectrum. These are your waves. And waves can get massive. Like radio waves. Look at those ones. 1,000, they can be 1 kilometer long. They can even be longer. Okay? And then what we've got here, microwaves. 10 to the negative 2 meters, which is a centimeter. Okay, and you just have a look here. These are the sizes of these waves. Like these waves here, radio waves, can be taller than a skyscraper. Okay, and microwaves are in about this range. They're maybe our height, maybe a centimeter. And you have a look here, infrared. And here we have the Roy G. Biv. Okay, here are the colored spectrum, the rainbow, red, orange, yellow, green, blue, indigo, violet, right? And these guys here are about in this wavelength, okay? About 10 to the 5, 10 to the 6 here. And then you get into ultraviolet, and then X-ray, and then gamma rays. Now, you have a look here at the wavelength. Okay, these are massive, like 1 kilometer long, and you see they start to get small. The wavelength starts to get smaller. And you see, when the wavelength starts to get smaller, like this is energy. So when you have one wavelength that's 1 kilometer, just one wavelength, not dangerous. That's why radio waves aren't dangerous. But you see now, as we start to compress these wavelengths, that's where we start to see more power, and that's where we start to see more energy. That's where we start to see things get more dangerous. And because you're compressing that 1 kilometer wavelength, now you've compressed it into 10 to the negative 10. And that's why X-rays can be dangerous, because you have so many waves within a certain given, a certain amount of X-ray there, that you're getting so much more energy bombarded into you. Gamma rays, they're the toughest. Okay, look at that. They're so 10 to the negative 12. I don't even know what that is. Is that a billion? 100 billion? Could be. In 1 meter. So these things here, massive amounts of energy. We'll get into frequency there in a second. A wave can be short and fleeting. So there's your wave pulse. And you see how it'll travel down the entire rope as long as the energy will maintain it there. The sound of a balloon popping, flash of a camera, bang. That's a wave pulse. Did you guys ever see in Beirut, Lebanon, I think that was last year, extremely devastating. There was, I guess for 5 or 7 years, they had been storing fertilizer down in the harbor area in Beirut. And This stuff is it's a derivative. It's a derivative of TNT, dynamite. This stuff is highly dangerous. Ammonium. And hi, Shire.
We have bagels, please.
Well, I'm talking. Say hi to everybody.
Hi.
All right. I'll make bagels after. Bye bye. Close the door, please.
No, okay?
Shire, can you close the door, please? Thank you. I love you. Bye. And anyway, yeah, that's Shire. He's trouble. I think I was talking about in Beirut there, it was a massive explosion. Like just a one-time boom. And yeah, it was devastating. It was horrible. You can go on YouTube and watch it. But there are other videos that are out there that of people 10 kilometers away, 20 kilometers away that that could see the explosion happen. But that wave pulse is still traveling. And then 10 minutes later, after the explosion, they're still filming. And then all of a sudden, this is I don't even know how many kilometers away. And boom, they could feel that wave pulse. Okay? But if you have many wave pulses, now you can actually create this continuous wave. And we call this there a sine curve, okay? And examples of this here, light from the sun, a tuning fork, you know that, it's just a continuous, okay, wave. This one here, this is a good slide here, all right? The formulas here are really not too bad. The mathematics here is really not too bad for this week. But I will tell you there's a lot of wordy definitions, okay? Like there's two kinds of waves here. There's what's called a transverse, which goes up and down, okay? Transverse waves, the vibration is perpendicular to the direction of the wave. So the wave is traveling this way. Okay, you can see right here, your velocity is traveling this way. But the vibration is going up and down. So a transverse wave, the vibration is perpendicular to the direction of the wave. Longitudinal wave, the vibration of the medium is parallel to the motion. So you see here, the velocity traveling in the same direction, but you'll see now, look at my wave pulse here, okay? It's traveling parallel to it, okay? So that is transverse, longitudinal. You'll see them again.
The motion of a transverse wave is perpendicular to the direction of energy flow.
Great slide, eh? Watch this one.
The energy of a longitudinal or compression wave travels in the same direction as the motion of the wave.
Outstanding.
The energy of a longitudinal...
Enough of that. This is waves in the real world, longitudinal and transverse waves in Japan, 1995.
The people in this video of the 1995 earthquake in Kobe, Japan, clearly react before the first large jolt hits. They have already felt the lower energy, but faster traveling, longitudinal P waves. The brunt of the earthquake's energy is brought by slower traveling transverse S waves.
So you'll see there that longitudinal waves are faster and usually less magnitude, not as dangerous. But then you'll see the slower moving transverse waves. Those are the ones there that cause the real damage. And then when we, I'll show you there a tsunami, the physics there behind a tsunami. It's one picture there, and you'll see it's kind of the same thing. All right, I'll show you those there later. Wave speed, The rate of movement of the disturbance is determined by property of the medium. And remember there that waves, they transfer energy to atoms in the medium, whether it's air or water or whatever, right? And or even Mother Earth. When an earthquake erupts somewhere, okay, the wave pulse is traveling through the stone underneath us, the Earth's crust. And you have to think that, look at air, okay? I'm speaking right now, which is causing a wave there to move. It's moving the air. Now, the air isn't really touching each other. So the energy is transferring to the air molecules, and then that air molecule then hits another air molecule, but it's got to move a bit because there's kind of empty space in there, and those guys are moving. But if you think at we can actually hear pretty well underwater because we make a sound, and the water molecules don't really have to move in order to transfer the energy. The water molecules are already kind of touching each other. So it's kind of you'll see there that waves kind of move faster in water. And they actually move faster in stone or cement because the atoms of stone or cement are actually touching each other. So it's a very quick movement. Oh, my son's coming back. Hi.
We have a bagel.
Okay, I told you I'd make you a bagel, but I gotta teach my class now. I'm coming. Give me a bit. Close the door. Thank you. My wife's the lucky one. She's out there working right now. Free. So that's an important idea to what that we'll cover again is the medium will affect the speed, and we'll show you that. Okay, the mass of these oscillating particles. Okay, the heavier the mass, the less they're going to move, right? And another determining factor is the forces that are acting between the particles. Aha, like we said, if air, the gas molecules in the air actually kind of have to move to get to transfer the energy to another gas molecule in the air in order for this wave to propagate. Not so much in water, and really not at all in stone, but we'll get there. What do we got? So, crest, trough, these are your nodes here, and here we have like a rope tied to a post, okay? And kind of like, you're doing like a UFC thing. So the speed is proportional to the tension. If your rope is really slack, you're really not going to get a good wave speed. If your rope is really tight, okay, you're going to get a good wave speed. And the speed inversely proportional to the mass. So if you increase the mass of the rope, of course you're going to decrease the speed of the wave. Okay. Couple of formulas here. So you consider a string of L, length L, with a mass m. The speed at which a wave travels in the string when it's under a tension F, there's your force in newtons. So here we have the velocity is equal to the square root of the force, okay, divided by P. And P is the mass per unit length, okay, mass per length. Really not too bad formulas here. You'll see them, you'll have to use them, but you can see there, it's just a matter of plugging and playing. And you can see the relationship here. I may ask for the velocity, okay, of the wave, and here I'll give you the mass and length of the rope, and you figure out P, pop it in here, divide it by your force, square root it, and there you get your velocity. Okay, not too bad. And here's an example here. A student stretches a slinky, and I realized this there last year. I had some people who weren't aware of what a slinky was. Slinky is a spring, kind of like a kid's toy. It is a kid's toy, and it's a spring. And you can put it down the stairs, and it flips and flops. It was kind of fun a million years ago. Okay, but a student stretches a slinky spring out on the floor to a length of 2 meters. The force needed to keep the slinky stretched is measured and found to be 1.2 newtons. Is measured. I'm going to update that. Thank you. Okay, so the slinky is stretched to 2 meters, and the force that is needed to keep it there is 1.2 newtons. The slinky's mass is 0.3 kg, and what is the speed of any wave sent down the slinky by a student? So I've given you there the mass of the slinky. I've given you the length of the slinky. You find P, okay, sub it in here, and away you go. And this is your velocity here, 2.8 meters per second. That's how these go. They're really not too bad. There are lots of review questions there that you guys can work on, and I don't think you guys are doing great. Doing really, really well. Keep it up. Keep it up. The sine wave, that's that wave there, like this. Okay, you have peak, valley, you can have crest, trough, however you like, it doesn't really matter. Remember, the amplitude is the maximum displacement of the peak or trough. You can have the magnitude there, or you can have the magnitude, doesn't matter, okay? The amplitude of the peak will equal the amplitude of the valley. So the amplitude there to the crest, to the top of the peak, should be the same as the amplitude down to the bottom of the trough or the valley, okay? And wavelength and cycle is an oscillation, which we're going to find out is called period with a capital T. Write that one down because that one's there for your lab, okay? Period is the capital T. There's a crazy formula in the lab. You don't use that formula initially to solve for period. You'll see there, Greg talks about it in the video. Okay, but basically, a period is one oscillation, the amount of time it takes for one oscillation. So you look at a grandfather clock, okay? That was one oscillation, okay? And the period is the amount of seconds it takes to do one oscillation. We'll get there. We got more, though, okay? Properties of waves. Here's an illustration of changing the wavelength or the amplitude. And you'll see here, this is my original wave, and you can see my magnitude. Okay, if we cut a line down the center, there are my nodes, there are my peaks or crests, here are my valleys or my troughs. Okay, we can calculate our wavelength, these kinds of things. The shorter the wavelength implies more complete waves fit into a given distance. So if we shorten the wavelength, these waves can get more dangerous because you've got more energy in a given space. Like, you remember those gamma rays? You've got 10 to the 12 wavelengths in a meter. 10 to the 12. Remember a radio wave? We have one wavelength in a kilometer. Not dangerous at all. Lower amplitudes, okay, they imply a smaller height. So you see, you can have waves of all different varying, okay, but all the properties still hold true. Period and frequency of waves. Here's another formula, okay? So the frequency is the number of vibrations or oscillations in a given time period, okay? So if an object undergoes one complete vibration in 1 second, then the frequency is 1 vibration per second. We use hertz. So hertz is just a word that means vibrations per second. That's all we're talking about, 1 vibration per second. So thus, a sound of 440 hertz means that 440 vibrations are hitting your eardrum every second. 440 hertz, 440 vibrations per second. Okay? Period. The time that it takes to complete 1 full vibration or oscillation. So the grandfather clock. Okay? If that took 1.2 seconds, then the period for the grandfather clock in question is 1.2 seconds. Okay? And you'll see there that there's a relationship between frequency and period. And they're just, comment on say flip. Okay? They're just the inverse reciprocal. Or sorry, just the reciprocal of each other. Okay? T can be calculated from F and vice versa in this formula right here. So the frequency is equal to 1 divided by the period. If you want to calculate for period, flip them over. And the period is equal to 1 divided by the frequency. Okay? So here's a little example. If an object makes 2 vibrations per second, okay, its frequency is 2 hertz. 2 vibrations per second. That means it has a frequency of 2 hertz. If we want to figure out the period, you take 2, drop it below the line. So now you have 1/2. Okay? So in order, and if you think about it, it kind of makes sense. If we have 2 vibrations per second, so in 1 second of time, and we have 2 vibrations. Okay, that's 2 hertz. But the period is telling us how long does it take to do 1 vibration. And if we get 2 vibrations per second is the frequency, well, the period to do 1 oscillation will be 1/2 a second. 1/2 a second plus 1/2 a second gives us the full second. Hertz is 2 oscillations there per second. So again, these two here are just flipped. If you have the frequency, you also have the period. Attention, okay? If I give you, let's say I'm asking for the period, but I give you the frequency. Well, if I give you the frequency, you automatically have another bit of information. If I give you the period, you automatically have the frequency. Write that down somewhere because you will need it. Okay. What do we got here? Another formula. So this is formula number 3, I think. And here we have velocity is equal to frequency times wavelength. Okay. The wavelength and frequency are related to the wave speed. And again, another rinky-dinky little formula. And you can see there's overlap. You see in this formula here, we have frequency. Here I have frequency. All right. And you can see here, maybe I'll ask for the velocity, but I give you something else. So you'll have to figure out another formula, get an answer, and then substitute it into this one. That's how it goes. That's why I put all the formulas right here. Okay? Because then you can see them. You can see the relationship. There's your frequency there. There's your frequency there. Okay? What else do we got here? Velocity. Have a look at these. You'll remember there, this formula here, this is from week 1. Velocity is equal to distance over time. I just flipped it around. It's the same formula, but distance is equal to velocity times time. So you can see there's overlap all over the place here. Test yourself. An electric car, an electric razor completes 60 cycles. Vibrations there per second. What is its frequency? And what is its period? 60 cycles per second. There are your hertz right there. And then to figure out the period, you just do the reciprocal. 1 divided by 60. And you'll see there, If we have 60 vibrations per second, all right, remember the period is trying to ask for one oscillation, how long does it take? And you'll see there that it's very small. Because in 1 second we have 60 vibrations. Well, one vibration takes 0.017 seconds. Okay. If the distance between a peak and a valley, okay, so here we're talking wavelength, right, is 60 centimeters. What is the amplitude of this wave here? We'll come back there to this one, all right, and you'll see that there is a bit of a relationship here as far as that one goes. Gusts of, I'll show you, I'll better explain this one there when I have a visual. Gusts of wind cause the CN tower to sway back and forth. And it actually does. In Sudbury, I don't know if anyone's there from Sudbury, but they have an enormous, I think it's, I'm pretty sure it's still there. They were talking about taking it down. 50 years ago, they had a smaller smokestack in Sudbury. It's a mining town, and it killed all the vegetation. It actually looked like the moon. NASA brought astronauts up to Sudbury in the 60s there to prepare for the moon landing. But now they have a 1 kilometer tall smokestack, and apparently this thing sways 2 or 3 meters at any given point in time. And but gusts of wind cause the CN tower to sway back and forth. It really does, completing one cycle every 10 seconds. What is the frequency and what is its period? Okay, again, cycles per second. Figure this one out. Number 2, I'll come back to. What do we got here? A water wave oscillates up and down 3 times each second, and the distance between wave crests is 2 meters. What is its frequency? Well, we have the number of oscillations there. We have the wave crests, and there's your wavelength. Let's read this again. A water wave oscillates up and down 3 times each second. Okay. Now, you're going to see these questions. Remember, the trouble is the English. You want to pull the math out and write it down on a piece of paper. So 3 times each second. Okay, so there's your hertz. There's your frequency. And the distance between each wave crest is 2 meters. So that's your wavelength. Okay? What is its frequency? What is its wavelength? What is its wave speed? So, right there, easy peasy. Right there, easy peasy. And velocity is equal to frequency times wavelength. So there's your velocity, 6 meters per second. And it works the same way for this one here. Apologies, okay? Try these out. Oh, a good thing to know, okay? The speed of sound is about 343 meters per second, okay? That's a good one to know. I didn't write it on the formula sheet, but that's a good one to know. All right? And try these out. Have some fun with these. They're really not that bad. All right? You're just pulling information out here. Your formulas are kind of limited. Now, you really don't have a lot of formulas there to play around with, right? Okay? So, try these out. Here's another one here. Before a concert, musicians tune their instruments to a note A, which has a frequency of 440 hertz. What is its wavelength of the resulting sound at the speed of the sound at room temperature is 344 meters per second. So, there you go. Plug and play. Inversion of a transverse wave. This one here you'll need to know there for the quiz and the test as well. And these next couple slides here I'll show you. So here we tie a rope firmly to a post. You initiate a wave, right? You flick your wrist and the wave pulse travels down. The wave has a front that always leads. What happens to the wave after it reaches the end of the structure? You see the wave here is traveling on top. It hits here and then comes back. If there's still enough energy left in it, it comes back inverted. Okay?
Suppose a wave travels along a string that is connected to a mass of infinite density. The wave cannot overcome the inertia of the mass. Consequently, no wave can be transmitted into the massive medium. Instead, the wave is completely reflected and inverted, but undergoes no change in amplitude, wavelength, or wave speed.
So, even when a wave can't travel through something, it actually comes back and through a medium which it can travel through. Okay. Where are we here? Yes. So reflection of a transverse wave here. So kind of the same thing. What happens to the wave after it reaches the structure? It stays up. And we'll show you this one here. Have a look at this one.
Suppose a wave on the string meets an open boundary where there is effectively no mass and therefore no inertia. No wave can be transmitted. The wave is therefore completely reflected with no change in amplitude, wavelength, wave speed, or phase.
So what we're talking about here is an open boundary. So basically, it's kind of neat. This rope thinks that the wave is actually continuing on here. And if you look at it, it kind of is, but just in the opposite direction, the only direction it can go.
Wave on the string meets an open boundary.
And you see, and then it kind of thinks that it's moving forward.
Where there is effectively no.
So that's on an open boundary. Here we've got a hard boundary. Okay. This is kind of interesting here. Interference of two transverse waves. So you initiate two upward waves going in opposite directions. And you see what's going to happen here? They're going to hit each other. And at one point in time, they're going to become one wave. So the energy from this wave is going to kind of mesh in some way with the energy from this wave. Now either they could cancel each other, or they could superposition themselves. And you have a look here. Here you have initiate two upward waves going in opposite directions. What happens to the waves when they meet? And you'll see here at this point, they haven't met yet, or they're about to. And you'll see what happens is, this is called a superposition, where the peaks are additive. Okay, so neither wave is affected, and for that split second, you have this superposition, because you have a positive wave and a positive, let's say a positive wave of 1 and another positive wave of 1, and in essence, you'll have, when they both meet for that millionth of a second, you'll have positive wave of 2. Okay, and we call this constructive interference. Okay, and both waves, they come out of it unaffected. Away you go.
When two waves add together to create a larger wave, they interfere constructively. The amplitude of the larger wave can be found by adding the amplitudes of the original waves. Constructive interference occurs whenever two crests or two troughs meet.
Okay, have a look at this. So if we do the same thing, but we invert one of the waves. So we have this wave here, negative. It's moving in this direction. Here we have a positive wave moving in this direction. You do get a superposition, but you'll see here, if they're equal in amplitude, for that millionth of a second, they cancel each other out. We call this destructive interference. But then you'll see, after that millionth of a second is gone, those waves continue on. There they are again. So this is what we call destructive interference.
When two waves add together to produce a smaller wave, they interfere destructively. The amplitude of the reduced wave can be found by adding the amplitudes of the original waves. Destructive interference occurs whenever the crest of one wave meets the trough of another.
Perfect. We have something there called a standing wave. You generate a periodic wave, okay, on the end of a rope with a fixed end. First wave pulse will reach the fixed end, and then it will invert. Remember, like before there, okay, on a closed end, it inverts, okay, and you keep doing this so on and so on until basically it looks like your bottom, okay, and so on until the wave appears to be standing still. And that's what it'll look like. It'll actually kind of look like that, but kind of standing still. There are your nodes again. And there's even a word there of an antinode. I haven't tested you on that one, so don't worry. If you guys can remember node, I'm happy. Okay. So nodes, these are regions where the waves create destructive interference. So you see here, there's nothing there. It's zero. So that's where the waves have created this destructive interference. And you'll see here antinodes there. There are regions with waves that create constructive, but don't worry about that. What do we got here? And this is applicable there to real life. And here we have a suspension bridge that's getting thrown around by the wind. And you'll see there the nodes, okay? There's a node at the end, a node in the middle, another node at the end, okay? It's kind of neat there to see. Diffraction, we'll deal more with diffraction there when we do light there on the last, I think it's week 12, okay? But you'll see here that you create a wave in water. That's all it is. You create a wave in water. Put your hand in the water and it creates a wave. The wave will change shape when it reaches this opening. And you see what happens is these are flat and they're just traveling forward. But what happens here is it'll hit here, and you'll see what kind of happens is that the walls of this opening, they kind of slow the wave down on the ends, so that the wave that was in the middle here is still going on, and you see how it kind of bends. And these waves can kind of go around a corner. All right. This is called diffraction. The bending of a wave is called diffraction. The amount of diffraction depends upon the size of the opening, of course. Opening larger than the wave, little diffraction. The opening is smaller than the wave, you'll get a massive amount of diffraction. Diffraction there, I don't think there's anything on the quiz, and I don't think there'll be anything there on the test as far as that goes, but you will see that word again in 2 weeks, 3 weeks, okay? If a tree falls in the forest and no one hears, does it really make a sound? I don't know. I don't. I would rather ask, if a tree falls in the forest, what type of wave does it make? And just the whole idea of sound. If there's nobody there to hear it, because remember, the wave is traveling through the air, and the air is propelling the wave itself, right? And then the air is moving, and it's kind of compressing, and that's what's causing a little bit of a pressure on my ear drum, okay? And that's how we hear. But if there isn't any ear to hear, what if there isn't any air? What's going to go on with that wave? Interesting stuff. Not much. Sound is a longitudinal wave that can travel through different media. So, sound waves are not transverse. They're longitudinal. Okay? Sound is produced when a vibrating object causes the medium to vibrate. Okay? So that's why you can have your teeth closed and you can hum. And you know, this is what is causing it. All right? That's what's causing the sound. Your teeth are vibrating, your skull is vibrating, you make a sound, the air is okay? So this is what's going on here. Sound waves have a certain velocity in air, 344 meters per second. Okay? That's a constant. But sound moves slower at lower temperatures. Like at minus 40, the speed of sound is only 310 meters per second. Why? Sorry, Harley. My beagle's right here. I think I disturbed her. Looking at me. But anyway, why would the wave move slower in colder air? Well, because the air isn't moving as fast, right? That's why. The air is colder, doesn't have as much kinetic energy within it, so therefore it's not going to be able to travel as fast as it would like to at normal room temperature. Sound travels faster in small molecular weight gases. So like hydrogen, helium, these really low molecular weight gases, okay, sound will travel a lot faster because it doesn't have to use as much energy to get through those atoms. And I got a couple of videos here that I'll show you. And I'm showing videos now. I've had enough.
Special K cereal now has 25% more almonds for when you're ready.
Sorry.
The average person spends 26
Seriously?
years and 3 months in bed.
Get out of here.
We love you.
Oh, this is really good.
We love your movies, but also you're an executive producer of this TV show that I love. It's called Through the Wormhole.
Yeah, yeah.
Sorry, excuse me. I apologize. I apologize.
Morgan Freeman.
Well, this is the Tonight Show starring Jimmy Fallon. So, with is pretty interesting, but starring in this. I love it. It's just got nominated for an Emmy. Congratulations on that. They do great stuff with that show. It's a great show. It's really, really fun. And I wanted, there's something you did on there that I wanted to recreate here, if you don't mind. Because I do love your voice, and everyone loves your voice. But I was wondering what your voice would sound like if you were on helium. So I thought maybe if you could.
Helium has a molecular weight of 2. Very, very, very small atom.
Way down, but these, if we would please.
Sorry, molecular weight of 4.
Conduct an interview, but before we talk, we'll just come on, Morgan, don't come on, cramp up on me now. Don't quit on me now, Morgan. Don't cramp up on me now. All right, I will hand you this guy. There you go. I'm gonna do it too. I love having you here on the show. It's so fun. It's so fun when you come here. You still sail on your ship? Remember you told me you have a sailboat.
No, I don't sail it anymore. Sell it.
I was gonna, because I never got the invite, and I always wanted to go on your ship because you know what I would call you?
It's a sailboat.
Sailboat, sorry. Do you know what I would call you? No. Captain Morgan. Alright, here we go, right?
Do you ever want to go to space? I really shouldn't be doing this.
All right. So what we're seeing there is that the waves are still being produced, and you see our voice sounds like this because we have air in our larynx, okay, our voice box. But if you replace that air with helium or something like that, now the wave can travel faster, and that's why Morgan Freeman's beautiful voice got changed. Have a look here. Here we have sulfur hexafluoride, a much bigger molecule.
The Subaru Outback.
Oh,
Equipped with
man.
advanced safety
I
features
hate
like eyesight
commercials.
driver assist technology and winner of the IIH.
Brutal.
Hey, you. Before I come in, you should know I have gas.
For the record, not your worst opening line.
Check it out. It's the gas I use in my free electron laser to support high voltages, but it also has an interesting secondary use. Here, breathe this in.
But before I do it, if you're a cop, you have to tell me, right?
Just try it.
What's it supposed to? Oh my God, it's so. You're a mean one, Mr. Grinch.
All right, so you'll see there that once the air has been replaced by this sulfur hexafluoride, the wave has to push this heavier molecule, okay? So therefore it can't travel as fast, so therefore that's why he sounded like the Grinch. Sound travels in helium at 1,000 meters per second. That's why I talk like this. Sound travels in the air at 344 meters per second. This is normal. Okay. And sound travels in sulfur hexafluoride at 133 meters per second. So that's why the voice went very low. Okay. Sound waves and other media. And again, we'll talk more about light waves there in a couple weeks, but sound moves faster in water. Okay? If you go back here, sound travels in air at 344 meters per second. Sound travels in water at 1,500 meters per second, because water, you don't have the space in between individual molecules like you do in the air. Okay? Water, generally the water molecules are touching each other to some extent. So therefore there, the wave can just zoom, go right through them because they're pretty much all touching. And if you look at sound waves can travel through like the Earth's crust, 5 kilometers per second, because those atoms in the stone, the granite, the Earth's crust, they are touching, and so therefore now the wave can just zoom. Okay? This is a shot there of what happened there in 2004. And you'll see there that there was a massive earthquake here. I think it was Banda Aceh, as I recall, right on the coast of Indonesia, on the main island there. And the wave, okay, it moved all over. And you'll see here, all on the eastern coast of India, Sri Lanka. I was in Sri Lanka and I saw the devastation there. Was I there 2010, so 6 years after, and they were still recovering, and it was quite devastating, the loss of life. And you'll see here that it hit on the eastern coast of Africa as well, and basically just about as strong as it, like, obviously the strongest, the most devastating effects were right here on the Indonesian coast, but on the Sri Lankan coast and the Indian coast as well, it's almost like it was just devastating. The wave did not really delineate and go down in any strength. And even on the eastern coast of Africa here, just massive, massive waves. And didn't really dissipate over time either. Okay? This is how a tsunami works. Here you have your long waves out in the middle of the ocean. Okay? But then as, the earth, the land, the ocean is kilometers deep, but then the land snakes up. It's almost like an underwater mountain. That's what we live on, right? And so basically the wave is running out of medium. Like the wave would rather travel in the water here, and what's happening is we're running out of water. So here is your wavelength here, from trough to trough. And then you'll see what's going on here is the wavelength has gone down. So when you compress the wavelength, what's going on with my magnitude? Yes, there's the devastation. Okay, these waves here out in the ocean. There was another, the same tsunami there happened in, because of that, happened in Thailand. And I read reports there that there were scuba divers that were 2 or 3 kilometers out into the ocean, and they were swimming around on some excursion, and they came back, and the whole place was destroyed because of a tsunami. Well, they didn't feel it out in the ocean, because out here the waves aren't bad. They just kind of went, oh, hey, what was that? But then, as the wave travels closer to the land, the wavelength compressed, the magnitude, the amplitude increased. Okay. Hearing and sound. This is what I want you to know from this one here. The cochlea. Okay, the organ for hearing. And see if I can zoom in a bit. And you have a look here. All right. So this is your cochlea here. Your middle ear. You got 3 ear bones here. You guys will get into it more in your biology, all right? But this contains fluid that resonates at input frequency, stimulating hair cells to fire more. The ear converts sound waves into mechanical waves. And this is what gets sent there to your brain. All right. We're almost done. Sounds are classified by their waveform. So here we have a pure tone. Okay, the sound with a sine wave, a tuning fork, a beautiful sound. You know, an A or an A flat, or a B, a C plus. All right. A complex tone is a sound with a multifaceted waveform. Okay. Any continuous wave that does not have a sinusoidal sine. Okay. Just a mishmash. That's all we're talking about there. That's called a complex tone. Pitch. Our subjective impression about the frequency of sound is called pitch. So a high-pitched sound comes from a high vibrating frequency. A low-pitched sound comes from a low vibrating frequency. And the human ear can hear pitches that range from about 20 to 20,000 hertz. Sound waves below 20 hertz, they are called infrasonic. We can't hear them. Sound waves above 20,000 hertz are called ultrasonic. We can't hear either of them, okay? But dogs can. We can distinguish between very quiet sounds that are difficult to hear to very loud sounds that may be painful to hear. Sound levels measured in decibels. We normally experience sound levels between 0 and 120. And be careful, the maximum is 120, but ear damage can happen well below 120. Well below. Okay? The tone quality of sound is used to distinguish 2 different sounds, even though they have a similar pitch and sound. A note played on a violin does not sound like the same note played on a flute. This is how we can distinguish who is speaking in a room, because we've recognized that everyone has their own tone quality. And you can see where these questions are coming from. These are just kind of this information here, the last 10 or so slides. It's more, there'll be a multiple choice definition question, or they'll show up in a matching. Okay. Doppler effect, you will see again. The whole idea is when you see a police car or an ambulance or a fire truck in the distance and it's coming towards you, it'll have a higher sound. And then as it passes you, and now it's going the other direction, it'll have a lower sound, or you know what I mean? That's what we call the Doppler effect. And this is an apparent change in the frequency. Is it a real change? No. But it's our position and the very fact that this siren is moving towards us and then eventually moving away from us. That we're not moving, it is moving, and this is the apparent change of frequency of a wave caused by the relative motion between the source and me. So an ambulance, police car, train, this kind of thing. The cause is the frequency increases as the source approaches you, and the frequency decreases as the source moves away. And I have a little pictogram here. And you see what's going on here. Like if you're standing, you're standing here, and the ambulance is coming towards you. See the arrow? The ambulance is coming towards. You'll see here what's going on. Look at my wavelength. Because this thing is propagating forward, the sound is coming forward. All right? The wavelength here appears to be shorter. Doesn't have to travel as far. But if you were on this side and the ambulance is moving away from you, you see here there that the wavelength, because it's moving away from you, the wavelength tends to appear longer, and that's why we get a different sound. The crest appears closer together in the direction of the source moves. The crest appears farther as it's approaching, or as it's moving away from you. So that's what we call the Doppler effect. Echolocation, if you're a dolphin lover, this is dolphins and bats, and surprisingly, a lot of animals use this. Okay, and where they're using their own sound, because sound will bounce, and because of that, I can tell how far away something is. Echolocation is a process of using sound waves and reflecting them off of anything to determine its location. Kind of like sonar, right? Basic echolocation uses reflection only. A wave is emitted from me, the dolphin. It goes out there into the medium. It hits an object, a fish. It's reflected back to me. I know where exactly that fish is. Or I know that this fish is over in this direction here. Okay? And the time between the emission of the wave and once it comes back reflected depends upon the speed of the wave and the distance. Okay. An example here, echolocation. You will need this principle, okay, for the quiz and the test as well. This is a great example. You'll see this one again. If you're standing on a cliff here and there's kind of a canyon, okay, and then there's a cliff over here, and if you shout at a cliff, okay, so you shout at it, rah, and that sound travels to the cliff, okay, it will come back. And, you can kind of hear this, right? So if you shout at a cliff and you hear the echo in 3 seconds, so it went and came back in 3 seconds. So 1.5 second, 1.5 second, right? So that's what we're looking right here. The sound took 1.5 second here and 1.5 second to come back. So if you shout at the cliff and you hear the echo in 3 seconds, how far away is the cliff? Well, if it took 1.5 seconds to get there, 1.5 seconds to get back, and the speed of sound is traveling at 344 meters per second, we use our formula. Speed is equal to distance over time. Flip it around for distance, plug and play, and that means that the cliff is 516 meters per second. It actually works the same there with lightning and thunder. Okay, you can count when lightning you see first, and the thunder is the sound there that the lightning makes traveling through the air, right? That bang sound, right? So you see the lightning, start counting, and then you can figure out how far away the thunder is, the lightning was when it struck, because then after a certain number of seconds, you'll hear the thunder. And you can calculate in meters pretty accurately, okay, based on 344 meters per second. That's the speed of sound. Applications of echolocation, ultrasound, radar, dolphins and whales. There's your fish. Bats, of course. Okay. This is a really good one. Just the whole idea of breaking the sound barrier. All right. traveling past 344 meters per second. Now you're traveling faster than the sound you're making. It's interesting. Have a look. Coming weeks, quiz 3 will open there. I could open it up right now. Okay. And it'll be the same thing. I've given you the paper copies now so that you guys can just work away on it. I'm hoping there by tonight or tomorrow I'll have the answer portal open and ready to go so that you guys can start uploading your answers. It's not that bad. Try it out because it is a precursor to next week's test. I'm trying to, because I haven't tested you guys on any of this stuff, so I'm trying to give you guys an idea of what's going on. I'll let you guys know the test is almost done. There will be true and false, multiple choice, matching, definitions. There are some calculations, but really nothing you guys haven't seen there before. Assignment 2 will open up next week, but you don't need to worry about it because it is based on test 4. Okay? And test 3 will open up there next week. But that's basically all we've got. That's all I got. I hope you guys are doing well. Let me know. Stick around. Is there anybody there? Yes, there are. Excellent. Joanna had to go. That's all right. Hey, man, if you guys got to go, go. You guys have busy lives. I got rugrats downstairs that are going to be screaming that they need food soon. So let me know how you guys are doing. I don't see any issues, major issues, but if there are, now is the time to let me know, because we have, what is it, week 9? This finishes week 13, so we got 4 weeks. We got a month until this whole ball of wax is gone. So if there's any issues going on, you need to let me know, because I can fix things now. I can't really fix them there the last week. I can, but it's let's get her going. I hope you guys are doing well. Just keep on trucking, and other than that, you guys just have a great day. I'll post this there to YouTube in 15 minutes. Thanks, guys. And you as well, Mallory. Thank you, Regan. Thank you, Taylor. Good to see y'all. Be safe. Get outside. Enjoy the nice weather. And I'm just going to stop recording, and if you guys have any questions, let me know.